All right, this is the very last section of this chapter that we're going to do. And this is section 13.4, and it's finding the slopes of tangents. You may see the word derivative in this section a lot, but we'll deal with that word derivative later. But tangents, you may remember tangents when you were in geometry, which was you had a circle, and that's supposed to be a circle. And a tangent was a line that just touched the circle once. I was supposed to touch the circle, I just missed completely. But that's the tangent that you probably are more familiar with. In the world of calculus, tangent also applies to functions. And there are two lines that we're going to need to deal with in this section. The first one is a secant, and a secant is a line that actually intersects a graph in two places. So if this is my graph, a secant would be something like that. I intersect the curve twice, right there, and this is referred to as a secant. Okay, a tangent, and this is kind of my own definition, it's a line that intersects the graph once without crossing the graph, or it just sits on the graph. And a tangent would look like this. So let's say I wanted to draw the tangent right here at that point. If I wanted to draw the tangent there, then what I'm going to do is come down, and it's going to be the line like that that just touches the graph at that one point. It doesn't go through the graph. It only touches it once. And when I say it only touches it once, I mean in that small area. Because if I were to draw a tangent right here, which I can do, that is going to be a tangent, and it's going to cross, it's going to hit like that. And locally, in that small area, that is a tangent, even though if I were to continue pulling this line across, it does intersect my graph a second time. So what's happening far away from the point of tangency doesn't matter. This is still considered a tangent. So these blue lines are tangents, right there and right there. Those are tangents. And this point right here is what you call the point of tangency. It's where the tangent hits the curve, the point of tangency. And what we're going to focus on is finding the slope of that tangent. So we have a blue one down here. We're going to find that slope. We're going to find the slope of that line. And it's really based off your old Algebra 1 slope of change in y over change in x. We're just going to do some crazy stuff to it. So the first problem, and I thought it would be best just to do an example rather than some vague math definition. Let's find the slope of the tangent to that graph, x squared minus 3x plus 1 at x equals 3. And I went ahead and graphed the equation. This is my function f of x. And that's x squared minus 3x plus 1. This is the tangent, that red line. And there's a point at 3. When x is 3, I go up, and that's the point of tangency. And I drew the tangent at that point. And that's the slope we're looking for. And it's a really steep slope. I'm expecting something around 5, 6, 7, maybe even higher than that. But it's a pretty steep slope. To find the slope, what we're actually going to do is we're going to start with the secant that shares the point of tangency. So I'm going to draw a secant that goes something like, I don't know, something like that. That would be a secant. And we're actually going to find the slope of that secant. We're going to ignore, what am I going to say? Oh, we're going to ignore the tangent for just a minute. And I'm going to start with the slope of the secant. And if you remember back in Algebra 1, the way we found slope was y minus y over x minus x. And so I need these ordered pairs. Well, I know the x coordinate of this problem is, of this point is 3. And to find my y coordinate, I'll just plug in 3. So f of 3, if I plug 3 in up here, 3 squared is 9. 3 times 3 is 9, plus 1. So that gives me a y coordinate of 1. So I know I have an ordered pair 3, 1. This point over here, I don't know what it is. I can see that it's some negative x, and the y is somewhere up here close to 2. But what I'm going to do is I'm just going to keep this very generic. I don't know what this ordered pair is. So I'm just going to say that x coordinate is x. And I don't know what the y coordinate is, so I'm going to call it y. Except instead of y, I'm going to call it x. And sometimes instead of y, we use f of x. I'm going to call it x and f of x, which is the same thing as saying xy. But that is some unknown xy ordered pair. And I'm going to find the slope between those 2 points. So my slope of the secant is going to be y minus y, so f of x minus 1 over x minus 3. f of x minus 1 over x minus 3, and that is my secant slope, and that's what we're going to start with. Now remember, I want the slope of the tangent. I didn't ask for the slope of the secant, so we're going to have to change this a little bit to turn it into the tangent. And the way we turn the secant into the tangent is we take this x-coordinate right here, this second point, and I move that point a little bit further to the right. And I'll move that point a little bit further to the right. And I'll move that point a little bit further to the right. And I'm going to keep moving that point to the right. And what's going to happen if I keep moving that point to the right is my secant, but then it looks like this. And then next time my secant hits those 2 points, it looks like this. As I keep moving that point to the right, my secant slowly and slowly looks more like the tangent. Slowly and slowly looks more like the tangent. And that's kind of weird. It's hard for me to graph it like this. That's a whole lot of stuff going on. So I've got this little thing right here that can kind of animate it. So I have my tangent is red, and I have this point right here is my secant point, and I want this x to move closer to 3. And so if I drag that second point closer to 3, the slope of my secant, if you look at that secant line, it gets closer and closer to the tangent. As x gets closer to 3, and follow my x up there, as x gets closer to 3, if I move closer to 3, I get closer and closer to the tangent. So here I'm getting really close to 3, and you see that green line has almost become, oh geez, now I can't find that point again. There we go. And then when I get to 3, boom! The tangent actually becomes the secant becomes the tangent. So we take that second point and we move it closer and closer and closer to 3. And when I move x closer to 3, the secant actually becomes the tangent. So in this problem right here, I'm looking at my secant, f of x minus f of 1. That actually represents the slope of my secant. But to turn that into the tangent, we take that x and we move it closer to 3. We take that x and we move it closer to 3. We take that x and we move it closer to 3. And we do that with the limit. So once I take the limit of this thing as my x gets closer to 3, this thing actually becomes the slope of the tangent. And once we set up the limit, then we start plugging in and we start solving. So I'll look around. Let's see, I have the limit as x approaches 3 of f of x. Whoops, I didn't mean to write f of 1 there. My bad, that should just be 1. So it's f of x. And I can look up here and I see that f of x is x squared minus 3x plus 1. So I'm going to take out that f of x, and I'm going to plug in x squared minus 3x plus 1. The minus 1 on the outside stays over x minus 3. And we're doing the limit of this as x approaches 3. And now it becomes a normal limit. We're just going to solve this the way we've always solved limits. X squared minus 3x plus 1 minus 1 plus 1 minus 1 is 0. I've got x squared minus 3x over x minus 3. And now we solve the limit. If I tried plugging in 3 squared is 9. Minus 3 times 3 is 9 over 3 minus 3. And we get 0 over 0, which means we have to keep working. So that doesn't make me too happy because I have to keep working. So there's kind of a frowny, smiley man. Oh, well. But this isn't too bad. X squared minus 3x, I can pull an x out on top. So I'll factor out the x. Leaves me with x minus 3 over x minus 3. The x minus 3's cancel. And all I'm left with is the x. So now I'm going to take the 3, I'm going to plug it in for x, and I'll just get 3. And that's actually what the slope of that tangent line is. That's a slope of 3. So there's my tangent slope. Now, when we're working these problems out, I am not going to expect you to draw the graph, draw the secant, and draw 43 secants showing the secant becomes. You don't have to do all of that. We're going to just set up the limit, and we're going to go straight from the limit. But the limit is we start with the secant slope, and then when x approaches 3, the secant becomes the tangent slope. And we got a tangent slope of 3, which seems pretty reasonable here. It's not as high as I was expecting, but that is a steep positive slope. Then the very last thing, how far are we here? 9 minutes, holy cow. Just give you a quick formula here. this is more generic. To find the slope of a line tangent to any function f of x at any x coordinate, x equals a, the slope is the limit as x approaches whatever the point of tangency, x approaches a, of f of x minus f of a over x minus a. And we'll work that limit out. We'll plug the function in. We'll plug in a, and we'll clean this up, and we'll solve that. And if you remember from about a week ago, a few days ago, that fraction right there, f of x minus f of a over x minus a, that is the average rate of change that we did earlier. So this is kind of pulling it all together. That's the average rate of change from earlier in this chapter. So we do the limit as x approaches a of the average rate of change of f of x minus f of a over x minus a. So that's what we're going to do, and we'll hammer this out a little bit more in class tomorrow. And that'll wrap up the chapter. Test is next Thursday. If you have any questions, come see me.